Welcome to section 6.1. Today's objectives are going to be to identify, name, and describe polygons and to use the sum of the measures of the interior angles of a quadrilateral. So we're going to come to a decision on what a polygon is going to be before we start using some of its properties. So we're going to say that a plane figure that meets the following conditions is a polygon. A polygon has to be formed by three or more segments called sides, and each side intersects exactly two other sides, one at each endpoint. So we want to look at what a vertex is in terms of our polygons. A vertex is just the endpoint of a side. So here we have the side RS, and the endpoints are the vertexes. So R is a vertex and S is a vertex. So let's figure out which of these figures are polygons. So figure A is a polygon because it has three or more sides, and each side intersects two other sides. So this side here intersects the side here, and if you go around to every side, you'll see that each side is intersecting with two other sides. Okay, so this is a polygon. So the next one is not a polygon. And it's not a polygon because it really only has two sides. Figure C is a polygon. It has three or more sides, and every side intersects with two other sides. Figure D is not a polygon because this side right here only intersects with one side. It's open here, so those sides aren't connecting. So we have yes, no, yes, and no. Here's a chart of the different types of polygons categorized by their sides. I recommend you pause the video now and copy these down. We're going to be working with these different types of polygons throughout this chapter and throughout the book. So there are two styles of polygons. They are convex and concave polygons. A convex polygon is considered convex if no line that contains a side of the polygon contains a point in the interior of the polygon. So what you want to do if you want to figure out if a polygon is convex is to extend the sides, and if none of the sides go into the interior of the polygon, then you should be good. It should be convex. So a concave or a non-convex polygon is the opposite. If I were to extend all these sides, I'd be good with all these surrounding the outside, but as soon as I got to this side and I saw that it went inside of the polygon, I would know that that polygon is considered concave. So for these two polygons that we have here, we know for this one that this one is convex because none of the sides will be going into the interior. Now, for figure B, we can see that this one would be concave. You can think about it as going inside of a cave. So you can think if that line goes inside of it, it's going to be concave. We have other terms that we can use to describe a polygon. We've used equilateral and equiangular before talking about triangles, so those two concepts still apply to polygons. And we have this term regular. Now a regular polygon is a combination of both. So it's equiangular and it's equilateral. So that means all the angles are the same and all of the sides are congruent. So let's decide whether these polygons are regular. So for figure A, we can see that this diamond looking shape is not regular. And it's not regular because although all the sides are congruent, only the opposite angles are congruent. So this one is not regular. For figure B, we see that these five angles are congruent, all five sides are congruent. So this polygon is regular. For figure C, this polygon, we know all the sides are congruent, we don't know anything about the angles. And we can clearly see that some of these angles won't be congruent. So, since we don't have enough information shown in our diagram, we conclude that it is not regular. So let's talk about diagonals. A diagonal is a segment that joins two non-consecutive vertices. So we know vertices are the ends of the side, so it needs to join two non-consecutive. When I mean non-consecutive, I mean it can't be, if we're talking about Q, the vertices that are consecutive with Q would be P and R. So non-consecutive could be any other one. So the non-consecutive ones, and we're still talking relative to Q, would be T and S. So it's a segment that goes from the non-consecutive vertices. So in this shape we have our polygon with a diagonal through it. So the question is, what two polygons can you see? Well, this one's being split through the diagonal. So we have these two polygons here. We have these triangles. We have triangle BCA and CAD. So now that we've talked about diagonals and different types of ways to categorize polygons, let's think about what's going on in the interior of a quadrilateral, which is a four-sided polygon. So this theorem tells us that the sum of the measures of the interior angles of a quadrilateral is 360 degrees. So any quadrilateral that you have, if you sum up the four interior angles, you're going to get 360 degrees. So in this example, we're being asked to find the measure of angle A and the measure of angle B. The theorem that we went over told us that the measure of the interior angles of a quadrilateral have to add up to 360 degrees. So I know if I add up these four angles, I should get 360 degrees. So we'll refer to our chart and put the corresponding values in. So we know A is 5x. The measure of angle B is represented as 7x. C is 50 degrees. And D is 70. And this should all equal 360 degrees. So at this point, we just combine like terms and solve for x. So 7 plus 5 is 12x. And we have 120 equals 360 degrees. So we have 12x equals 240 degrees. And x is going to equal 20. But that's not our final answer. We need to find the measure of angle A and the measure of angle B. So the measure of angle A is represented as 5x. So we do 5 times 20, and we get 100 degrees. And we have to find the measure of angle B as well, which is represented as 7x. So we do 7 times 20, we get 140 degrees. And we can always check our answers because 100 plus 140 gives us 240, and 240 plus 50 and 70 will be 360. That's the end of today's video. Once again, thank you, and I'll catch you on the next video.